Hello everyone, my name is Aijia, third-year doctoral student at Sidma University under Professor Dang. This time I'm going to introduce my research topic, the application of wave propagation in high-rise buildings for detecting damages combined with deep learning. I'll explain the contents from the following parts, including introduction, methodology, current results, conclusion, and discussion. Firstly, why it is necessary to monitor the status of high-rise buildings and detect damage after earthquake. On the one hand, from the perspective of structural health monitoring, monitoring and evaluating the structural situation to detect existing damage or to avoid potential damage are needed, which can extend the service life of structures or prevent building collapse as much as possible. Especially for high-rise buildings, structural health monitoring is also important. These two figures show the extremely crowded due to people unable to back home after Tohoku earthquake, which happened in 2011. Even though the ground motion was not very strong in the Tokyo central area, where seismic intensity is about 5, but still many people found it difficult to bike home and had to stay in the city all night. It caused traffic jams and telephone congestion. Therefore, the fast method of evaluating high-rise buildings after earthquake is available. With the speed development of technology, fast detection and human saving becomes a desirable goal. A lot of new techniques were introduced to detect damage and achieve the evaluation of buildings. For example, the method of using computers to detect damage based on digital image processing was proposed. One of them is the vision-based structural health monitoring technique. The image of structures or bridge were considered as the input data used to train the model. And in this slide, these two figures show the UAVs used to detect the components of structures where people cannot arrive. In addition, an image-based 3D model also was used. This method utilized photos taken from different angles to create 3D models of structures. This method can then be analyzed to detect deformation or change over time, providing suggestion for the health of the structure. Generally, some sensors will be set up in buildings to record seismic response data like acceleration, displacement, and so on. Then processed data will be used to detect and localize damage of buildings. This slide shows the main components of structural damage detection systems. The response of building to earthquakes, typically analyzed from vibrational perspectives, can also be analyzed from wave propagation perspectives, which have been proved mathematically equivalent, as shown in this slide. Over the past few decades, vibration-based method and wave propagation-based method have widely used to detect damages of buildings. For vibration-based damage detection method, which is based on the structural physical properties such as mass, damping, and stiffness. Stiffness can affect its dynamic response. It means that damage will without the structural stiffness changed. By analyzing this change before and after damage happened, people can identify or locate structural damage. But this vibrational parameter will be affected by some environmental parameters like temperature. So some research proposed using wave propagation method to detect damage also. However, this method also will be affected by some soil structure interactions. So the important thing that extracts the building seismic response itself from the soil structure interactions. So in this research, the conclusion calculation was introduced to solve this problem. First of all, the building should be assumed as a one-dimensional model. Shear deformation is believed to be the most important contributor to a building deformation. Therefore, shear beam models can be used to identify and monitor the status of buildings. The layers of a building were numbered from top to bottom, each layer characterized by a thickness h, mass density rho, shear modulus mu, and shear wave velocity beta for I equal 1 to n. Actually, the model will excited by the shear vertical wave and the shear horizontal wave. So what is a shear vertical wave? It is the vibration direction of shear as a shear vertical wave is vertical to the propagation direction and in the vertical plane. This means that as a shear vertical wave can cause vibrations in the z direction and y direction both. For shear horizontal wave, the vibration direction of shear horizontal wave is only in the horizontal plane and vertical to the direction of propagation. It means that shear horizontal wave only cause vibration in the y direction, so it simplified the calculation. Therefore, only shear horizontal wave will be considered as excited wave in this research. Secondly, how do we extract a building seismic response from the coupling of the building to the soil structure? The decollusion method was introduced to solve this problem. Here show the basic equation of deconvolution of two signals U1 and U2 in the frequency domain, given by equation 1. So here, to avoid a very little value of denominator case, epsilon was plus to the denominator to avoid a very little value of denominator. And in this research, the water source was assumed as the roof. So in the equation 2, we use UT instead of U2. T means water source as the top. So the essence of deconvolution calculation is the ratio of the signal at different floors to the top floor after Fourier transform. Thirdly, what is the result after deconvolution and why the water source was put as a roof in this research? Here is an example of deconvolution waves at different layers. Deconvolution with waves recorded as the top floor. It can be seen that the propagating path of deconvolution is simplified when the water source is located on the roof. It only consists of one causal upgoing wave and one causal downgoing wave. Therefore, the water source was placed as a roof in this study to simplify analysis. Finally, how can we detect damage from deconvolution results? In other words, what is different between the deconvolution results of damaged case and non-damaged case? For damaged case, as shown in this slide, the wave will not propagate following a straight line. The stiffness will be decreased cause damage occurred, so the propagating wave will be reflected by interflow of buildings. You can see the middle figure. Here is a interference phenomenon appeared in the interflow caused by damage. So this phenomenon, this interference will result the chaos of deconvolution results. So this feature is used to recognize the structural damage. Here we use time window to process the seismic response. After time window sliding from the beginning of recorded response to the end, the time sequential impulse response can be obtained in all time domain. It obviously presents the character for different situations like damaged or non-damaged is different. For the damaged case, the propagating path is not a straight line, but for the is a chaos of deconvolution results, but for the non-damaged case, the propagating path is a straight one. The flowchart of proposed damage detection method using wave propagation approach combined deep learning method is shown in this slide. In short, this method is separate as two steps. One is training data generation based on MDF model. The other is a CNN-based damage organization. Here, the deconvolution results as input data to train same model, and the output data is the prediction results of the status of building behavior. This method was applied in a 1-to-3 scaled 18-floor steel frame test on a shingle table. The test data could be downloaded from NEAT, which is open access data. This slide shows the detailed information of shaking table test. The result of shaking table test was carried out to analyze the feature of impulse response, that is, deconvolution result, before and after damage, and used to build the multiple degree of freedom model, that is, MDF model, based on the test specimen for generating numerical data for training the model later. Here, two kinds of data I use examples to represent damaged situation and non-damaged situation, that is case 40 and case 250 respectively. For case 40 is the non-damaged case, the building in the elastic status, but for the case 250, here is a breakout beam end appeared in the building, so it would be considered as damaged case. For case 40, elastic status of buildings, the deconvolution results as shown in this slide. The first row figure are the seismic response of the top floor and the second floor. It means that the seismic response of second floor deconvolved with the response at the top floor, processing by sliding window from the beginning to the end, like this. Then the middle figure displays the visualized results calculated with a sliding time window. Finally, the third row figure visualizes the deconvolution results by mapping data to a color space, where larger value correspond to lighter color. Then, for damage case 250, the deconvolution results seem like I explained before. The layer stiffness decreased due to damage occurred, so the propagating wave will be reflected by the interflow, resulting in the chaos phenomenon in the deconvolution result as shown in red circle, highlighted in this slide. How is the deep learning being used in damage detection? Firstly, it should be built multiple degree of freedom model based on shingle table test specimen to generate numerical data for training the model later. Then, the trilinear model rather than bilinear model were used to simulate the nonlinear response of buildings to generate seismic response. In addition, 80 ground motions downloaded from KNet database as input ground motions to simulate seismic response, and the level of ground motions adjusted from 0.1 to 3 scaled. To investigate the accuracy of the model with different kinds of input data, raw data and image data were input to train the model respectively. This slide shows examples of raw data of deconvolved waves and image data of deconvolved waves. Actually, for raw data of deconvolved waves, it is a value matrix of deconvolution result. The flowchart of CNN model training is shown in this slide, including 4 steps totally. First step is database generation based on MDF model to generate numerical data and to train the model. Second step is training the model with different neural networks, convolutional neural network like AlexNet or RedNet. The third step is evaluation of the model with numerical data generated by MDF model. Finally, we should test the accuracy of trained CNN model with real data generated by shingle table test. Okay, now let's see the result of trained CNN model accuracy and discussion. This slide shows the training result with different kind of input data and different kind of convolutional neural network to compare the accuracy of same model under different architecture of convolutional neural network. AlexNet and RedNet was adopted in this research, and compare the results between the raw data and the image data. It should be noticed that the same model shows significantly higher accuracy in telling image data compared to raw data. The rules of raw data for the same purpose achieved an accuracy of 84%. It also required more epochs for training, and which in turn increased the training time. In contrast, for image data, the predicted accuracy of the model is more than 95. The result is better than the raw data. The accuracy of trained model should be tested based on shingle table test, that is real data. So here we use configure matrix to test the accuracy of trained model. This slide shows the configure matrix results of predict and actual labels using shingle table data under a different kind of input data and a different kind of architecture of convolutional neural network. Compared the results between the raw data and the image data based on the different neural network. Obviously, the test accuracy of raw data only 81%, but for the image data, the test accuracy achieved more than 96 to 98%. This could be due to the extents outlined in the raw data, so which potentially impacts the judgment of the same model. And these misclassified figures can be contribute to the extents of evanescent waves at the beginning of deconvolved wave figure, leading to the misclassification. Therefore, to avoid such some inaccuracy during the training data generation, we can cut off this part, this initial segment, it could be useful. The proposed damage detection method, a wave propagation approach combined with deep learning, can achieve the automatically recognizing the damage and non-damage of buildings. And then the deconvolution results can be used as a feature to identify the status of the building. In addition, it should be noted that when using image data as input data, to predict the accuracy is higher than use raw data, raw data, and the test result achieved more than 98%. So it demonstrates that this proposed method is useful to evaluate the status of the building after damages, and it also can be used to do a structural health monitoring after earthquake happened. Thank you for your listening and your time.